Good evening everyone. In today's video we are going to see regarding the shear. So let us see what do you mean by shear. Shear is nothing but it is a term used when two sections on either side of a plane in a member have tendency to slide along that plane. So if you see the figure, this is one section we have, this is another section we have. So these two sections, they have tendency to slide along this plane. So this is what we call it as a shear. So now why it is caused? It is caused due to these forces. This is nothing but shear forces which is going to act in an opposite direction. If you see this, it is acting in upward direction, this is acting in downward direction. So these forces, what they do, they try to shear off a section. So this is what we call it as a shear. Then next, let us see shear in the structural member. So the structural member may be subjected to shear force due to either flexure, punching or torsion. So accordingly it is classified as flexural shear. Due to flexure it is called as flexural shear. Due to punching it is called as punching shear, and due to torsion it is called as torsional shear. So now let us see one by one what do you mean by these. First one, we'll start with flexural shear. So the shear associated with the change of bending moment along the span. So it is known as flexural shear. Usually if you take a beam, so in that we are going to have a shear that is nothing but the flexural shear. So it is due to the change in the bending moment along the span. So due to this, what happens that beams will be subjected to flexural shear. So generally we call it as a shear. That is nothing but the flexural shear. This is due to the change in the bending moment along the span. Next is punching shear. So this is nothing but the shear associated with punching a thin member by a concentrated load is called as punching shear. So for example, if you take one slab and if you have one column here, only one single column, so the area of this, what you can say, if you take this as a footing and if you take this as a column, so this column is resting on this footing. So if you see area of this is very less and the area of this is very large. So due to this concentrated load, what happens that this section will be subjected to shear, right? The shear associated with punching a thin member by a concentrated load, it is called as punching shear. So when you will come across these type of cases, that is, one is when you are going to have a concentrated wall load on a slab. The next is a beamless floor slab supported directly by the columns. So generally we have a framed structure, that is slab, beam, column and footing. So if you don't have beam, if the slab is, for example, if this is the slab, if this slab is directly resting on this, or you can say column, then next what happens that this will be subjected to the punching shear. This is nothing but associated with thin members and the concentrated load. So or otherwise you can have a footing slab carrying a concentrated column. If you see, we will be having this footing, and at the center somewhere here we have the column. So this will also be subjected to punching shear. Generally what happens is that if you take this footing slab, it will be subjected to both, what you can say, flexural shear as well as punching shear. So flexural shear is referred as one-way shear and punching shear is referred as two-way shear. A footing slab carrying the concentrated load is subjected to both these type of shear. So flexural shear is referred as one-way shear, punching shear it is referred as two-way shear. Then next is torsion shear. So when a member is subjected to torsion, it is subjected to the torsion shear. So now let us see what is the effect of shear. So let us consider one beam AB we have, which is simply supported, we have, and this is the neutral axis we have. Then next it is subjected to the UDL. Then next is, let us consider what you can say 3 sections within this beam. So I will take below this neutral axis, we will take one section somewhere here in between. The next is at the center we will take another support. Let us take one what you can say element, that is 3. So generally if you see the bending moment and shear force of this simply supported beam with UDL, so at the center we will have maximum bending moment and shear force will be 0. So at supports what happens is that bending moment will be 0 and shear force will be maximum. So this general concept we have. So if you take one element, so like this is element number 1, if you take this element and if you see, this element will be subjected to what you can say bending stresses as well as shear stresses. This is bending stresses and shear stresses if you consider this element 1. Then next is, if you consider element number 2 at this place, if you consider one element, so what happens is that, as you know, bending moment is maximum and shear force is 0. So therefore you don't have, and shear force is 0. So therefore you don't have shear now. So shear will not be there. Only you have to have the bending stresses. That is, it will be maximum, sigma max. So if you see, we don't have any shear, only bending we have. So due to this, what happens is that this will try to pull the section and this will try to tear off the section. So due to this, what happens is that the cracks which are developed will be vertical. This is at the center. Similarly, when you take section at support 3, that is at support, that is 3, if you see the element, so at the support what happens is bending moment will be 0. So therefore here we don't have any bending. So only we have the shear, tau c max we have. So due to this, what you can say shear, so this what happens is that these two shears, what they do, they will try to pull this section somewhat like this. Similarly these two will try to pull off this section like this. So due to this, what happens that there is a cracking in the member or that element. So these are nothing but diagonal cracks which usually develops at 45 degree. So this is nothing but element number 3. So therefore generally if you take one simply supported beam with UDL, so you can find that if there are cracks, so therefore what happens that at the center you can see that the cracks are vertical. So that is nothing but flexural cracks. Then next, somewhere here in between we will have flexural shear cracks. So at support it will be developed at 45 degree. So this is how what happens that the beam cracks and it is going to fail. So this is the effect of shear supported beam with UDL. We will see this shear stresses. The distribution of the shear stresses in RC beam is complex. Just hence, for the sake of simplicity, the nominal shear stress tau v is calculated as follows. In the IS 456, they have given in the clause 40.1 how to calculate the shear stresses. So therefore, first one is nominal shear stress. This is given in the clause 40.1 of IS 456 2000. So nominal shear stress in a beam of uniform depth, it is given by tau v is equal to Vu by B into D. So this tau v is nothing but nominal shear stress. Vu is nothing but the shear force due to design load. B and D are nothing but the cross-sectional dimension of the section, whether it is a rectangular beam or whether you have a flanged beam. So this is given in IS code in the clause 40.1. So let me show you. So here they have given, you can see here IS 456 2000, that is limit state of collapse shear they have given. So nominal shear stress tau v is equal to Vu by Bd. V is nothing but shear force due to design loads, B is breadth, D is the effective depth. This is for uniform depth. So if you are going to have varying depth of the beam, then if you see this figure, so the beam depth it is varying. So here it is less and at the fixed support it is more. So if this is the case, how to calculate the shear stresses? So it is given by Vu plus or minus mu by d into tan beta divided by b into d. So where mu is nothing but bending moment at the section, b and d are nothing but the cross sectional dimension, beta is nothing but the angle between bottom. So this is nothing but angle between the top and bottom edges of the beam. So now here if you see we have two signs, plus or minus. So when to use plus and when to use minus. The negative sign is used in the formula when bending moment increases uniformly in the same direction as the effective depth d increases and vice versa. So if you see here cross section also it is increasing, if the bending moment is going to increase in this direction, then what happens that we are going to use the negative sign or vice versa. This is for beams with varying depth. Previously it was beams with uniform depth. So for example, if you see here they have given beams with varying depth. So this formula also already they have given, and what notations they have taken, that also everything is being defined. Then next is design shear strength of the concrete. Design shear strength of the concrete. Design shear strength of the concrete. It is given in 40.2 of IS 456. The design shear strength of a concrete in a beams without shear reinforcement is given by tau c. It is given by tau c, that is nothing but design shear strength of concrete without shear reinforcement. So shear capacity of the concrete is given as tau c, which is given in table number 19 of IS 456 2000 for particular tension reinforcement. So if you refer this also, they have given in table number 19. So in table number 19, design shear strength of concrete tau c they have given for different grades of concrete. So you can see this table they have given, that is nothing but from this you will come to know design shear strength of concrete tau c. Then next is the concrete shear capacity. It is given by Vc is equal to tau c into b into d. Tau c into b into d. This is nothing but concrete shear capacity. Then next we have another term, that is tau c max. Tau c max. So this clause is very important. You have to remember this. Under no circumstances the nominal shear stress tau v should not exceed tau c max. So we have this term, that is the maximum shear stress. So previously what formula I had shown for tau v, this tau v should not be greater than this tau c max. If it is greater, if the tau is greater than tau c max, we have to revise the section. We have to revise the section. So now what is what you can say tau c max value? So for different grades we are going to have tau c max value, which is being given in table number 20. So if you refer what you can say this here at the bottom, they have given in table number 20 maximum shear stress tau c max for different grades of concrete. Tau c max values they have given. Under no circumstances the nominal shear stress tau v should not exceed tau c max. Tau v should not exceed tau c max. If it is going to exceed, we have to revise the section. Then next is what minimum reinforcement we have to provide. Minimum shear for reinforcement, that they have given in clause 26.5.1.6. When tau v is less than tau c, minimum shear reinforcement shall be provided. When tau v it is less than tau c, minimum shear reinforcement. So this formula already it is being given here in this clause. Into SV should be greater than or equal to 0.4 divided by 0.87 f of y. So where ASV is nothing but cross sectional area of stirrups leg effective in the shear, that is nothing but cross sectional area of stirrups. B is nothing but the width of the section. SV is nothing but the stirrups spacing. F of I is the characteristic strength of what you can say steel, that is stirrups we have. So minimum shear reinforcement, this much has to be provided. Then next is design shear reinforcement, which is being given in clause 40.4. If, for example, if tau v is greater than tau c, then shear reinforcement shall be provided. If tau v, if it is we have tau v, if it is less than tau c, if this is the case, this has to be done. Minimum shear reinforcement has to be done. Minimum shear reinforcement has to be done. If tau v, if it is greater than tau c, then next these conditions have to be done. If tau v, if it is greater than tau c max, if it is greater than tau c max, then this will be like wrong. So you have to revise the section so that you take care that tau v should not be greater than tau c max. These are the conditions which we are going to follow ultimately, right? When tau v is greater than tau c, shear reinforcement shall be provided. So now how shear reinforcement is being provided? It is being provided in terms of vertical stirrups or bent up bars along with the stirrups or inclined stirrups. So let us see now one by one. What do we mean by vertical stirrups? So these are nothing but the steel bars vertically placed around the tensile reinforcement at suitable spacing along the length of the beam. This is the beam we have. So in the previous videos only we used to draw this, what you can say, reinforcement. So here we never used to draw these lines, what we are seeing now, these lines which is holding these bars. So this reinforcement we call it as a stirrups. The diameter of this stirrups, it may vary from 6 mm to 16 mm. So the next is the stirrups. The free ends of stirrups are anchored in compression zone of the beam. So you can see in the compression zone of the beam, these are being anchored to the anchor bars or the compressive reinforcement. If it is singly, you will have anchor bars. If it is doubly, you may have anchor bars, what you can say, compression reinforcement. So to that it is being anchored. Depending upon the magnitude of the shear force to be resisted, vertical stirrups may be one-legged, two-legged, four-legged and so on. So if you see, this is the section, only one leg you can see, one leg we have. This we call it a single-legged stirrup. So if you see this section, cross section, here we have two legs. Therefore it is two-legged. So here we have four legs. Therefore it is four-legged stirrup. Similarly we have 6, 1, 2, 3, 4, 5, 6. Therefore it is called as six-legged stirrups. Then next, it is desirable to use closely spaced stirrups for better prevention of diagonal cracks. So at supports and all, you may have due to tension cracks develop. So therefore it is desirable to use closely spaced stirrups. So therefore what happens is that the spacing of stirrups near the support is less as compared to spacing near the mid span, since shear force is maximum at support. So what happens is that generally if you see, stirrups less near the support and it is more at the center, maximum at the center. Why? Because shear will be less therefore at the center, so therefore it is more at the support. So therefore spacing of the stirrup we are going to keep it as less near the supports. So this is what you can see, this is the figure, these are the reinforcement, and this yellow color line what you are seeing, these are nothing but the stirrups. So if you see this actual, what you can say, beam sketch itself, so you can see now these top bars we have, we call it as hanger bars. So bottom if you see, we have tensile reinforcement. So this vertical bars what you are seeing now, which is running here, so the vertical bar which is running here, so this we call it as a stirrup, this we call it as a stirrups. The next another type is we are going to provide the bent up bars along with the stirrups. So stirrups. So if you see the figure, so here this is top reinforcement, bottom reinforcement. So they have provided the stirrups, that is vertical stirrups. But additionally they have provided, what you can say, this bent up bars also. So this is used when we are going to have the heavier shear force. If we are going to have heavy shear force, then we may go for these type of reinforcement or stirrups. So these bars are, why these bars are bent up now? So as to resist the diagonal tension. And whenever we are going to do bent up of this bar, we have to maintain the symmetry on both sides. So for example, like we have 4 bars now, 1, 2, 3 and 4 bars. So 2 bars you can take, do bent up, and 2 bars you have to run it straight. The next is inclined stirrups. So if you see the figures, you can see we have inclined stirrups. So if you see the figures, you can see we have the inclined stirrups. So that is used to resist the diagonal tension, and they are provided throughout the length of the beams. The next is shear reinforcement shall be provided to carry shear equal to VUS is equal to VU minus of tau C into B into D. So what happens is that the shear reinforcement what we are going to provide, it has to resist this much shear force. So why this much now? VU is nothing but total shear force minus of tau C into B into D. Tau C into B into D is nothing but the shear strength of the concrete. So the total shear minus of shear that can be resisted by the concrete, what remaining shear we have. So for that we are going to provide the shear reinforcement. So for a vertical stirrup, ASV into D divided by SV. So if it is inclined stirrups, it is 0.87 f of I ASV into D divided by SV into sin alpha plus cos of alpha. So where alpha is nothing but angle between the inclined stirrups. So when we are going to provide the bent up bars, so it is given as VUS is equal to 0.87 f of I into ASV into sin of alpha. Then next is what should be the maximum spacing of the shear reinforcement. That is being given in this clause 26.5.1.5. The maximum spacing of shear reinforcement in a member shall not exceed 0.75 D. 0.75 D is nothing but effective depth, 75% of effective depth for vertical stirrups, and D for the inclined stirrups at 45 degrees. In no case it shall exceed 300 mm. So this clause has to be taken care.